These are the notes for Unit 4, Day 3, and it's kind of a continuation from yesterday. They start on page 9 of your packet. We're still talking about straight line motion, and we're still decoding calculus problems. So our essential question is not changed here. We're still using those critical reading skills and those average strategies to figure out what the question is asking, and then what solution we need to apply given our definitions and our knowledge of calculus. Okay, so in today's focus, we're really focusing on, let me back up here. I think it says it, oh, maybe it doesn't. We're really focusing on then in these notes is relative motion. I was trying to find the term here. So it's a really common scenario. Let's say we've got two objects, in this case, two people, and both objects have their own position, velocity, and acceleration. So they're moving relative to one another. Okay, and this is where sketches are often useful, and often justifications and reasons involving discussing two parameters because two things are moving. So let's look at some possible scenarios here of relative motion. So this is a really common question, when do the two objects have the same velocity? Okay, so we know same velocity means their velocity values match. Not only their magnitudes, but their directions. So if object A has a velocity of -3, then object B needs to have a velocity of -3. If the question was, when do they have the same speed? Then one could be positive, one could be negative. But they're asking for specifically velocity. They want them at the same speed, going in the same direction. So that's one way to express it. The velocities are equal. Another way to express it is to solve this and set it equal to 0. So subtract VB from both sides and set it equal to 0, which would be this one, right? Minus VB, so the right-hand side is 0. Actually, I'm going to do a quick change of rule here because this will reinforce what I am trying to say. Let me take this and put it over here because that's really reinforcing what I'm trying to say. So I can subtract VB from both sides, and if I do that, then I get VA minus VB, and over here I get 0. That's this one, VA minus VB equals 0. Or I could subtract VA from the left side and put it on the right. So I get VB minus VA equals 0. So those are the three ways that we can say they have the same velocity. And which one we use kind of depends on the problem. Sometimes if we're just given two position functions, and we differentiate each one and set them equal to each other, then we can find the time at which they have the same velocity. Sometimes it helps to subtract them, take the difference of the two and look for when their difference is 0. Sometimes it helps. So it's just a matter of what is easier mathematically. Okay, let's look at some scenario here. Increasing and decreasing distance. That's another really common question. When is their distance increasing and when is their distance decreasing? Okay, and so often we can use, before we get into that, often we can use these expressions as justifications. So when do they have the same velocity? So you could say something like, oh, they have the same velocity when time is equal to 2 seconds because VA equals VB, or because the difference in their velocities equals 0. Okay, so these become justifications, which is kind of nice too. It's just reinforcing the math. Okay, let's say Bob is behind Abigail. So here's Bob, here's Abigail, and the distance between them is the distance between them increasing or decreasing? So let's set up a scenario for each. So let's say this is Bob's velocity, VB. It's really long. That indicates he's moving really fast. Let's say Abigail's velocity is smaller, so that's this vector is really short. And so physically speaking, we know that Bob is going to catch up to Abigail. Okay, so that means the distance between them is decreasing. So Bob is behind Abby, and Bob's velocity is greater than Abby's velocity, so the distance between them is decreasing. So that's how we would write a justification. So for this scenario, what we would do, let's say we started out with a position function, we would differentiate their position functions, and we would see at a particular time that Bob's velocity has a bigger value than Abigail's, and they both have the same sign. So in other words, either they're both moving in the positive direction or they're both moving in the negative direction. And so then we can use this as a justification. So conversely, if we can also write that as a mathematical expression. We can use the words, or we can use the mathematical symbols as a justification. Doesn't matter which one. So the other scenario is, let's say Bob is moving really slow and Abigail is moving really fast. Maybe she wants to get away from Bob for some reason, I don't know. But now it's very apparent that Abigail is going to be scooching forward really fast, and this distance is going to be increasing. Bob's not going to be able to catch up. So we can apply the reverse logic then. Bob is behind Abby, and Abby now has greater velocity than Bob. So the distance between them is increasing. And so we can say that, this difference is going to be decreasing. Okay, because this difference is going to be negative because her velocity is bigger. Or if we put it this way, then this is going to be increasing because, again, her velocity is bigger. So we can write these things mathematically, or we can do them, the justification in a more of a paragraph or a written form. Doesn't matter. Of course, these values we find by differentiating the position to get a velocity function, and then we plug in the times to get velocity values, just like we were doing in the previous note session. Okay, so that's when they're moving in the same direction, right? Let's talk about when they're not moving in the same direction. So in this scenario, they're moving, are they moving towards or away from each other? It's kind of obvious. They're moving away from each other here and towards each other here. So it's a little more obvious, right? These scenarios towards and away was a little less obvious. It's more like, will Bob catch Abigail or not? But the justifications kind of change now. So if they're moving away from each other, what we'll see now is the fact that they have different velocity signs, right? This previous page, we were looking more at the values because the signs would be the same because they're both moving in the same direction. But now the signs are different. So now our justifications is that Bob is to the left and Bob has negative velocity, so Bob is moving left, and Abby is moving right. So the justification is that they're moving away from each other because those scenarios are set up. And then conversely, if we look at these velocity values, we can say, well, Bob is to the left of Abby, Bob's velocity is positive, so Bob is moving to the right. Abby's velocity is negative, so she's moving to the left. So they must be moving towards each other because of their opposite signs. So it takes a little more to justify when they have opposite signs, but it's a little less math because we just know that they have opposite signs. We've stated that in the calculations. Okay, so when we get in the classroom, we'll go over those takeaways, and you'll continue on your problem solving with the motion questions.